In manufacturing, every step after a part is initially formed, machining, finishing, or plating, adds significant time and cost. Plastic processing bypasses these steps by producing highly intricate parts at net shape, meaning the component emerges from the mold in its final usable geometry. Compared to metals, plastics melt at significantly lower temperatures. This reduces the energy required to run a production line and simplifies how the finished products are handled immediately after forming. But before a part can be manufactured, the machinery must be matched to the underlying chemistry of the polymer. Plastics fall into two main categories. On the left are thermoplastics, where polymer chains can be melted and reformed smoothly. On the right are thermosets, which undergo a chemical curing process, forming rigid, irreversible cross-linking bonds. Because their molecular structure remains unchanged by heat, thermoplastics can be repeatedly melted and frozen.
This reversible phase change makes them uniquely suited for high-speed automated systems, which is why they account for over 80% of all plastic products manufactured today. The dominant industrial engine designed specifically to exploit this reversible chemistry is the injection molding machine. This process scales across a wide range of part sizes. A single machine type can be calibrated to produce a 50-gram electrical housing or a 25-kilogram automotive bumper. Regardless of the part's size, the production velocity is extreme. A complete manufacturing cycle, from raw pellet to solid geometry, typically takes only 10 to 30 seconds. Injection molding operates as a specialized thermomechanical system, utilizing the physical properties of thermoplastics to achieve rapid mass production. The core engineering challenge in this process is twofold: continuously converting solid polymer pellets into a homogeneous liquid melt, and then forcing that highly viscous fluid into a microscopic geometric cavity under extreme pressure. This schematic shows how the machinery is built to solve that problem. An injection molding machine is divided into two primary opposing sections: the injection unit on the left and the clamping unit on the right. Looking closely at the injection unit, the process begins when raw plastic pellets are gravity-fed from the feed hopper directly into the heated barrel. Inside this barrel sits the most critical internal component responsible for material preparation, the reciprocating screw. The screw has two distinct mechanical functions. First, it rotates. This turning action physically mixes the polymer, while the friction generated by shear force, combined with the external barrel heaters, homogenizes the plastic into a fluid state. Once enough plastic is melted, the rotational function stops. The screw then performs its secondary, linear function. It acts as a mechanical ram, plunging forward rapidly to inject the melt past a non-return valve. While alternative architectures like two-stage pre-plasticizers or plunger-type machines exist for specialized applications, the single reciprocating screw remains the industry standard. The injection unit solves the complex material preparation problem by combining thermal heating, mechanical shearing, and high-pressure ramming into a single moving component. Ramming that highly viscous plastic forward creates massive internal outward pressure. Without an equal counterforce, that fluid pressure would blow the mold completely open. That counterforce is provided by the clamping unit on the right. Using a stationary platen, a movable platen, and thick tie rods, this system holds the two halves of the mold in strict alignment.
These clamping mechanisms must provide a specific tonnage, a precise amount of closing force to resist the injection pressure. The specific mechanism chosen depends entirely on the required size of the machine. There are three main architectures used here. Toggle clamps provide high speed and mechanical advantage for low tonnage applications. Hydraulic clamps offer flexible stroke control for higher tonnages. And for the absolute largest production requirements, hydromechanical clamps are utilized. Inside the mold, the molten polymer follows a specifically designed series of internal distribution channels to ensure uniform filling across the entire geometry. The initial flow path dictates that the melt travels from the injection nozzle directly into this thick primary channel, called the sprue. From the sprue, the fluid flow splits and travels horizontally through secondary pathways called runners, which direct the melt toward the individual part cavities. Right before the plastic enters the final part geometry, it hits the gates. These are intentional, narrow constrictions that restrict the flow, allowing engineers to dictate the exact pressure and speed at which the plastic fills the cavity. As this dense polymer rushes in, the displaced air inside the cavity must instantly escape. It is pushed out through microscopic machined vents or ejector can clearances to prevent incomplete fills or burning from the diesel effect. Achieving a consistent net shape requires both the extreme mechanical restraining force of the clamping unit and the delicate fluid dynamics engineered into the mold. The entire injection molding process is executed in a continuous 4-step cycle, where maximum efficiency is achieved by tightly overlapping these operations. In step 1, the movable platen actuates, and the mold is closed and locked under high tonnage. Step 2 is injection. A shot of milt is forced under pressure into the cold mold cavity, freezing instantly upon hitting the steel. Step 3 overlaps with the cooling phase. Crucially, while the part cools inside the mold, the reciprocating screw begins rotating and retracting, actively preparing a fresh batch of polymer for the next shot. Finally, in step 4, the mold opens and the internal mechanical ejection system fires, pushing the solidified, net-shaped part off the mold core. Engineering this level of continuous synchronization, from the complex runner geometries to the high-tonnage molds, requires immense upfront capital. A single steel tool can easily cost hundreds of thousands of dollars. Despite these tooling costs, the rapid, overlapping cycle times make injection molding a highly viable method for mass-producing millions of identical parts. This entire continuous system, however, is useless for thermosets. Because thermosetting plastics undergo permanent chemical curing, they cannot be repeatedly remelted inside a heated barrel. For thermosets, we use compression molding. First, a solid charge is loaded into the heated bottom mold. The upper half comes down to crush the charge, while heat triggers permanent curing. Once cross-linking completes, the mold opens, ejecting the hardened part. Compression molds are significantly simpler and less expensive to build, and they produce less scrap waste. However, they suffer from much longer cycle times and substantially lower overall production rates. Compression molding perfectly solves the chemical limitations of thermosetting materials, but by directly leveraging the physical properties of thermoplastics, injection molding achieves a speed and scale that remains the standard for modern high-volume manufacturing.